Good morning. I'll admit when I was first invited to give a talk, my intention was to give my routine system on a substrate lecture. But when I saw the caliber of the other speakers, I really thought, well, this is not going to be good enough. I know many of the other speakers, I know the really high standard of what they're doing in industry. So fortunately, Helen was very kind and let me do a slightly different talk, completely new, which is looking at really the history of millimetre waves, where they came from, where they're going, how did we get to where we are now? Because I really think it's timely, because 5G, everyone's talking about millimetre waves. It really does seem that millimetre waves is suddenly going to become a big consumer product. So it would be useful to see just how long it's taken to get to that point, all the different steps that were taken along the way, particularly with some bias, look at some of the UK efforts that were made in the pioneering days, and then pose the question about what 5G and millimetre waves really means at the end. So I probably have too many slides. I haven't rehearsed, so I may go over time. I'll try not to. I'm sure Helen will come and poke me with a stick. And I'll dash through some of the historical ones very quickly just to give a flavour of what they're about. So firstly, why millimetre waves? I'll keep this simple. It's been known for many years that millimetre waves have the advantage for communications of very high bandwidth. You can make small, high-gain antennas. And as I talk to my own students about, for example, car radars, you wouldn't be able to sell car radars if you needed a satellite dish on the front of your car. The real reason for going to millimetre waves is not about fog or rain or anything. It's about antenna size to get high resolution on the radars. And there are potentially some special sensing capabilities. Although generally speaking, from what I see in the terahertz regime, there's a lot more potential going well beyond the terahertz for things like medical sensing than there is in millimetre waves. So those properties have been well known for many years, and you'll see various charts of loss, propagation loss at sea level versus frequency from the ITU, for example. And because of that characteristic, which you really can't change, then naturally certain frequencies have evolved as particular ones of interest. So there's a huge amount of interest in 60 gigahertz for example, indoor communications, where you deliberately want small cell sizes, very rapid frequency reuse. There's been a lot of interest over the years in W-band radars, because that's one of the windows in loss. And there's occasionally been talk of using 180 gigahertz for very small picocellular communications. And generally speaking, beyond a couple of hundred gigahertz, most technologies seem to be running out of steam. So there's been much less interest, except in very specialist applications. And of course, there's a window here at 30 gigahertz. That's been very often talked about for wireless communications, both on the ground and up to space. But I think it's very important to remember that this graph exists, because that's a very fundamental limit. You can't fantasize about using some of these applications, for example, for satellite communications, because of the massive amount of absorption by rain clouds and so forth. So you have to remember that this graph is very, very fundamental. So as I said, there's been a lot of interest in millimetre waves for decades, really. We go a whistle-stop tour through some of the early millimetre wave technology. This is not intended to be an authoritative historical summary. It's a very quick look at some of the techniques that we've used over the decades. And the very first kinds of millimetre wave amplifiers were, not surprisingly, based on 3-5 materials using the transferred electron effect. What's remarkable is the very first millimetre wave amplifiers were using entire wafers of gallium arsenide, basically ramming the wave into a wafer, getting a negative resistance effect and reflecting back a stronger wave. That's just how sort of brutal that first attempt to make millimetre wave signal sources was. But of course, very successful. And remarkably, there was a great deal of interest in using millimetre waves. Here there's 50 to 60 gigahertz being used at Bell Labs to do basically trunk communications, buried waveguides under the ground. Of course, now we take it for granted that that would be optical fibres, but they weren't invented then. Lasers were a dream. So here, for example, is some work at Bell Labs, where they built the entire test facility, very famous, called Home Bell. And you can see here the layout of the plant outside. They had remarkably low losses. Now, you probably know, some of you, that I work on substrate integrated waveguides. Here, this helical waveguide is able to achieve 2.3 dB per mile attenuation. And I kid you not, many substrate integrated waveguides are more like 2.32 dB per centimetre. That's staggeringly low loss. And something I didn't realise, the chap who actually got the Nobel Prize for inventing the optical fibre was one of the people that worked on those millimetre wave waveguides. So there's a couple of snapshots from the Nobel lecture, which was celebrating the work of Charles Cowell. And his very early work actually was on corrugated waveguides up in the millimetre wave regime for wide bandwidth communications. So as interest grew, then not surprisingly, people started to work a lot more on solid state devices. There was a very heavy emphasis in the early years on gun diodes, impact diodes. Just picked out a few examples of publications. And very deliberately, with some bias, I picked out some UK examples. This one from Plessy at Caswell, of work by George Gibbons, who was very, very famous at Caswell. And you can see one of these very specialist gallium arsenide impact devices in 1972. This one caught my eye. These are waveguide components screwed together. But even though this was 40 years ago, I reckon you could still publish that. If you actually made a millimetre wave transmitter receiver and made some measurements of, say, a QPSK spectrum, you could probably publish it somewhere. So that was really very pioneering, although, of course, as we'll talk about later, perhaps that's not particularly economical. And remember, everything was analog. And yet the engineers were so skillful, so good at their craft. I won't go through the whole detail. This is a 60 gigahertz system for making measurements of propagation, to measure rain fading. They made some really quite sophisticated electronics. Even though nothing was digital, there was no computers available, really. So tremendous skill in making sophisticated analog systems. And next, I overheard in the distance people gossiping about 5G, about how it's about the customers, what they want. And here's a classic example of something that was so advanced, so ahead of its time, tragically nobody wanted it. There was actually a successful trial of video phones in the UK and in the US using millimetre waves under the ground to connect up many, many voice calls, many video calls. Very, very successful trials, but they didn't get enough customers to make it viable. And of course, I guess the quality perhaps wasn't there. People thought it was just a gimmick. Well, that was way ahead of its time if you think about it. On your phones now, we all talk through Skype or FaceTime. You go, well, this is fantastic, how can we live without it? But then, nobody wanted it, bizarrely. So this is remarkable, looking back, 17 gigabits per second going down the millimetre wave waveguides. And something to note, you don't read about this very often. In the terahertz regime, remember I talked about the graph of atmospheric absorption, even on an optical bench, the losses can be so high you can't make a measurement because of water absorption in the air. And they were well aware of that, even at millimetre waves then. Much longer distances, their technique was to pump dry nitrogen into the hollow waveguides to get rid of the air, reduce the loss. One of the things about 5G is, of course, putting communications everywhere. I thought it would be useful to give some credit to Holger Meinl, very famous German professor who did really pioneering work in millimetre wave in Germany, and he put millimetre wave communications links on trains. right back in the 80s. Going back to the UK, I was impressed with this, just in passing, from ERA technology. Again, there's lots and lots of people trying to make all sorts of different kinds of waveguides on substrates for millimetre wave integration. There, they did some very pioneering work on 60 gigahertz thick film printed waveguides. You really could publish that now if you did that work from scratch. Very, very good pioneering work. Then, of course, gallium arsenide transistor technology started taking off. That's one of the very first millimetre wave gas FET amplifiers, as you can see in waveguide form. That was in the US. At Caswell, they were still really pushing the envelope of the impact diodes, gun diodes. I picked this one out because it happens to have two of my old bosses on, Ian Edison and Mike Brookbanks. And I thought they deserved some credit for their pioneering work. But also, note, this is 60 gigahertz, although it's an old-fashioned typewritten slide. They were getting more than 1 watt back in 1981. I'm willing to bet there are people in this room who would love to get 1 watt at 60 gigahertz. That's not trivial, even 30-odd years later. 1 watt at 60 gigahertz is not easy to achieve, certainly not cheaply. Planar antennas are, of course, extremely important for millimetre waves. So I picked out one of the very earliest works on a patch antenna array from Weiss. Very nice piece of microstrip patch antenna. Really, really elegant radiation pattern. And again, you really could publish that now. That was how good that work was. You could still publish that as such a good result. There was lots of work on innovative antennas to make an omnidirectional millimetre wave antenna for mobile communications. Cover some of that again later. And then one really crucial development, which I think was at the back of my mind when I decided to do a historical talk, was a British achievement, and it was the world's first gas mimic. Now, I've had this photo in my slides for years. I was given that by Jim Turner many years ago. But actually, if you get the old paper off the internet, you find this is the photograph in the actual paper. So I'd love to find out what the truth is. Ray Pengelly has some comment on Microwaves 101 about the photo not being the actual chip. So it could be Jim Turner gave me the right chip. If anybody knows, I'd love to hear. There's also a discrepancy about the year. Microwaves 101 claims it was 1975. But I've held the paper in my hand, and it definitely says 1976. And that matters, because next year could be a big 40-year anniversary of gas mimics, which I'm sure mean a lot to many of the people in the room. So that really was a revolutionary turning point. And then there's a whole series of achievements in gallium arsenide IC design. Just picked out a few examples. Some of the first amplifiers beyond 100 gigahertz. And something I think someone will remember in the room. One of the very biggest achievements in wireless design at the time was the single chip transceiver. I'll embarrass Liam. It was Liam Devlin and his group at Caswell. I remember this because first it was one of the most sophisticated chips anybody had ever seen in gallium arsenide. And secondly, when David Williams showed it working at a conference with a very simple wireless link, really, he got a massive standing ovation. And that is always useful because it's like 1993, not long ago. And yet just the idea of having, it was actually a wireless barcode reader, of having that data transfer from here to another room, got a standing ovation. And yet we take it for granted now. Go on Facebook. Why is my sat-nav not working? We take all this stuff for granted, but this is only just 20 years ago or thereabouts. And that's how our industry works. Sudden revolutions, and we suddenly go, oh, we couldn't work without this. And I think that's very relevant to 5G. So as I said, millimetre wave wireless communications was some kind of holy grail to get these very, very high data rates. I've picked out a few examples of UK work which I was familiar with. I may have missed some, and I'm more than happy to hear of other examples. One I'm very aware of, because I worked on it partly, was at BT. They had a system called M-Cubed VDS. And this is, I guess, a kind of well-known thing now. It was the idea of streaming a lot of video to houses through a broadband millimetre wave link. The so-called last mile problem, which at the time was a big challenge for the network infrastructure people. And they, believe it or not, actually fabricated their own MMICs at Martlesham. They did some really great work on 30, 40 gigahertz transceivers. Also at BT, Dave Wake's work was very well known. He took a slightly different approach, very focused on fibre radio techniques, which are starting to get adopted in various distributed antenna systems. He was one of the first people that talked about 180 gigahertz for very, very small picocells. Very near here, there was a really big buzz about Radiant Networks building this very innovative internet connection system using a mesh network wirelessly. It had these really quite sophisticated antennas with steerable dishes, so mechanical steering effectively. That sadly didn't come to a successful conclusion. The BBC were very keen on getting wireless cameras for sporting events and so forth. They took part in the big European project called MBS, the Mobile Broadband System, and they did indeed successfully build 60 gigahertz wireless cameras. And last, and probably least, I have to confess, I also worked on 60 gigahertz wireless communications when I was at King's College. We worked with DRA at Malvern. They were, of course, particularly interested in sort of battlefield communications, rapidly deploying networks and so forth. So we worked with Caswell's Foundry on various MMIC chipsets. We worked a lot on sectored antennas, as they're called, which is effectively selective diversity in different beams. But tragically, with the benefit of hindsight, we spent a huge amount of time modelling what's called delay spread, looking at multipath propagation, desperately trying to fight multipath by having clever steerable beam antennas. And I just regret so much that I didn't think of the idea of MIMO. Because MIMO is so genius. You actually use multipath to your advantage and send different data across different reflected signals around a room. Very, very clever. So sadly, I don't have that tremendous piece of impact. And if you look here, this is one of the very earliest Pembroke conferences. I've not been to that for a long time, but I'm told, this is my old supervisor at Gvarmy, was the founder of Pembroke when we were at King's College together. It's now a big global conference. So I didn't invent MIMO, but I did do the first T-trolley at Pembroke in London. That's about as big as it gets in terms of my claim to fame. So onwards. There's obviously then this very dramatic uptake of wireless technologies from 1995 to where we are now. I was very bad at history at school. I really didn't like it. It's taken me 40 years to realise how important it is to look back, because it makes you understand where you are now a lot better. We've had a really explosive growth of wireless systems. And in some ways, tragically, if you're from the gallium arsenide community, you have to accept that's been fueled more than anything by silicon RFIC technology. Stunningly cheap technology for very sophisticated electronics. And that's been necessary because, as I'm sure many of you know, the network operators, the consumers, the Nokias of this world, that's a bad choice, the Apples of this world, they want really, really low prices because they're selling millions or sometimes billions of these things. They want staggeringly low prices. So the whole world has changed. Transfer of manufacturing has been quite dramatic. And there's been a big consolidation of companies. It's not mine, I think. And I'm sure you've seen it yourself, even now. Big companies that you cannot imagine suddenly merge. For example, Corvo just being created. And it's a sign of our industry. The scale has become so large. To be one of those companies really supplying the Apples and Samsungs of this world, you've got to be big to cope with the volumes. And that's something we need to recognise. So given that we went through this 20 years of massive revolution of silicon RFICs, an explosion of wireless technologies, everyone has iPhones, let me pose the question, why didn't we have millimetre wave communications earlier? If it's such good stuff, the wonderful bandwidth, small antennas, what stopped it actually happening already? Now I've come up with 3 ideas. I'm happy to think of others, get suggestions. The first one is obvious. If you look at traditional millimetre wave components, they're just too expensive for anything remotely like an iPhone. Far, far too expensive. Cost of hardware has been a big barrier. And I think even now there's, in the 3.5 world, there's big challenges to match the very, very low cost that you can get on big silicon wafers in big foundries. Second one is a bit more subtle. Remember, a lot of the early trials were things like video phones, trying to get a lot of voice communications down a waveguide. Sneakily, another group of engineers took a different approach, and they did tremendous advances in video compression techniques. And I think that kind of postponed a lot of that, that's not me, that postponed a lot of that desperate need for more bandwidth, because you're able to get extremely low data rates, good quality video. And I couldn't find the real video, but I distinctly remember there was a video going around keynote addresses of various conferences of some kind of dung beetle rolling a ball. And it's hard to imagine, but that was the first time anybody showed a video on a computer. And that wasn't that long ago. Anybody remember that? Please help me find the original, because none of my colleagues thought I was talking sense. I remember it as clear as day. And finally, I have mentioned this before, remembering theoretically the need to go to millimetre waves is to get higher data rates, as well as reducing data rates with video compression. Another group of engineers, who I've already touched upon, had a genius idea of using MIMO. And if you look at 4G, LTE Advanced in particular, there's no millimetre waves, but the data rate is staggeringly good. Very, very clever stuff. A lot of signal processing going on, multiple antennas. Very, very clever stuff. And that again has delayed, I think, the need to really go to millimetre waves. Because at the end of the day, nobody will use an expensive technology if they can avoid it. So all of those things really, in many ways, are linked to the really explosive growth of silicon capability. So you've all heard of Moore's law endlessly. I like to show students my graph of Moore's law, not on a log scale, but extracted manually as a linear number of transistors versus year. And I will admit it's been tweaked a little bit, because there's a whole host of processors over here in the current generation that don't have more than 1 billion transistors. That's because there are other factors like speed, power consumption, cost that they need to consider. So since 2010, there hasn't been a desperate need to get more and more transistors on the chip. It's been about other factors. But these are real components, generally typical desktop processors, and you can see again that explosive transition. Digital electronics suddenly taken over the world. The internet, wireless communications, has really been very, very sudden. And in the microwave, millimetre wave world, of course, you also have to recognise that continual push with a huge amount of R&D funding, the silicon roadmap, has not just pushed down the size of transistors to get more on a chip, get more memory. As the transistors get smaller, they also get faster. So this is now a log scale. The node size goes from a few microns down to currently 14 nanometers. And this is only an estimate from a number of published results. But the FT is already pushing up near a terahertz. So silicon really can do millimeter waves. Where, of course, it struggles is generating significant power. So then if we look back at 3.5 technologies, I've put affordable in quotation marks because that's all, of course, a matter for debate. I've just picked out a few examples. Where we are now with mobile phones is a few watts, a couple of gigahertz. I think they're extremely low cost now, comfortably achievable. If you push into the millimeter wave regime, then a world record in 2013 was a mere 500 milliwatts. Slightly more recently, at 300 gigahertz with an HBT device, 10 milliwatts was published. Now, these really are the best I could find. And of course, the reason it's doing that trend is that transistors have this natural 1 over f squared power performance drawback, if you like. You really struggle to beat that challenge of the 1 over f squared performance. So even if we moved, say, to some, as we'll talk about, some kind of multi-chip module with most of the transceiver in silicon, but a few 3.5 devices to get more power, really, millimeter waves is really struggling to get any sensible power out of the transistors without even worrying about the cost. And that leads to a very important conclusion, which is now, I think, well documented, is that in terms of communications, steerable antennas are really important. There's just not enough power available. You've got to focus it in the direction of your receiver to get a sensible EI-RP. So again, with the benefit of hindsight, that was obvious. But it was Samsung that had the audacity, is that the right word? The bravery to say, we have done the world's first 5G trial. And actually, it wasn't millimeter wave. If you look closely, it's 28 gigahertz. It's a technicality. But a very nice piece of work. 64 antenna element arrays, steerable beams going across about 2 kilometers, giving a gigabit per second of wireless communications. And that set the whole industry, academia, racing, talking about 5G. So given what I said about the cost of millimeter waves, particularly in terms of getting power, do we really think millimeter wave communications will make it into consumer products? Well, they already did. I'm sure many of you know already. 60 gigahertz wireless HDMI, 60 gigahertz Wi-Fi is already available. It's not widely adopted currently. So there's a wireless HDMI link, which very clever, uses a number of steerable beams. So if there's an obstacle, it will deliberately bounce the signal off the ceiling. So there's a simplified block diagram of the chip. It's got these fairly simple beam forming networks to steer the beam in different directions. There's the circuit board with a big silicon IC and a ceramic antenna array. And tragically, that was in 2008, 7 years ago. I have to say, with relatively modest university funding, I stare at this all too often and wonder, how can we possibly do anything better than that? This is some kind of pinnacle of technology, I would suggest. And yet, unfortunately, if you look at the current generation, for example, from Intel, they've pushed the integration level even further. They now have a tri-band wireless Wi-Fi for simplicity module, which does include the 60 gigahertz band, gigabit per second data rate. And it's a tiny module stuck in the back of a laptop, say hiding behind a screen. And it's going to be ridiculously cheap. By our standards, as microwave, millimeter wave engineers, that will be ridiculously cheap. And of course, silicon is the thing that's made that happen. And I think it's really important to recognize just how good silicon technology has become. This is just one example from a PhD thesis at Berkeley. of a 380 gigahertz radar chip in silicon. I might, right, I'll hurry up. But of course, as we all know in the room, silicon can't do everything. When you look at more sophisticated transceiver systems that need more power, maybe in a base station, much more stringent filtering requirements, then you need a combination of active device technologies, silicon, gallium nitride, gallium arsenide, all sorts. You need a whole raft of different passive components, which are very difficult to replace. So the talk I was thinking of giving was all about multi-chip modules, system in a package, system on a package, system on a substrate. All really just different bandwagons for the same idea, that you take a whole raft of different technologies and put them on the same substrate. And I really do think that's the most important way of making a modern system of any kind, because you can buy the components from anywhere. It's important not to obsess about one technology versus another, just buy the right component for the job. That's currently going to a next level in many research projects, looking at so-called heterogeneous integration of silicon and 3.5 devices, either on some kind of common substrate or actually putting different deposited layers on the same silicon chip, which I think is probably a bit expensive. There's also projects looking more at the passive structures, so I won't go through that in detail, but these steerable antennas are a very, very important part of these MIMO systems. I'm really not convinced that you could make a transceiver with 64 different integrated circuit transceivers, one on every patch antenna, because that's pushing the cost just a bit too far. So the idea here is to make the substrate more intelligent and do a lot of that work in terms of beam steering and so forth. But fundamentally, I would pose the question, rhetorically of course, do we need millimetre waves? Why do we need 60 gigahertz uncompressed video, for example? And I think the reason there is a big wave of technology about to hit us, and very similar to the video phone in the 70s and 80s. But I think this time people will want it if the technology gives the right product to the customer. So yes, we need millimetre waves. We want high data rate communications, miniature radar, miniature sensors, because I think they're really going to fuel a big explosion in new forms of human-computer interaction, a big part of which is augmented reality, as it's called. So you've seen, this is obsolete now tragically, but you've seen this kind of stuff. You're walking down the street and you're given visual guidance on the current, in that case, status of the underground. If you're working, say, in a factory or as a mechanic, you've got on-screen guidance through your Google Glass, whatever the current terminology is. If you're a surgeon, you could be working in some remote country with relatively poor facilities, but you have computer guidance helping you, a lot of training from the computer, and so forth. So yes, to me is clearly the answer. And if you haven't seen it yet, I would really urge you to look at last week's Microsoft HoloLens demonstration on their developer conference video. That's the kind of thing I personally, as a video gamer, haven't had time for a long time. I've been waiting for that for years. You may see this kind of thing, augmented reality Quake, that went back maybe 15 years. Well, that's really going to happen, and that's the kind of thing consumers will buy. Now, I said 5G is sort of setting everyone into excitement in academia, in industry. All my communications colleagues keep asking me, will 5G use millimetre waves? And I think most of you in the room will already know the answer is obviously yes. Because firstly, it already does. Even 4G is using wireless backhaul up to E-band. We've already looked at 60 gigahertz Wi-Fi. So obviously, 5G is going to use millimetre waves. And 5G, I really think, is in some ways being undersold, which might sound unlikely. You see, for example, this vision from the European Commission of 5G, doing everything from smart grids, connected home, hospitals, intelligent cars, entertainment. It's not just 3G with a bit of a higher data rate. really do think 5G is going to be something very distinctive and new. And one of the advantages I have as a head of department is I see research, teaching across the whole spectrum of engineering, not even just electronics. I meet energy people, healthcare people, all these things. So much research going on, so much that 5G can do to make computers and humans interact more effectively. And these are all things, I think, which are really important for society. And the IEEE has this strapline to represent that importance of what we do. So finally, I have finished. I think what they're asking is the wrong question. In terms of 5G and millimetre waves, the real question is whether we're going to see this vision of lampposts with massive MIMO transmitters on, following you down the street, sending you a gigabit per second. That's the question. And that's why I'm posing it to you. That's why we're all here, really, is to discuss the future. That I'm less convinced about, because I'm not convinced that's going to be cheap. Okay, thank you.